Hello, my name is Fredrik Linder, and I am the Erlang lead at Machine Zone, which is the white and green thing down there. Machine Zone delivers highly engaging social real-time multiplayer games for the mobile market. And we have a few top-grossing games on the iOS market. Okay, picture this, that you are you're having a game night with some of your friends. You get over there, you pack up the board game, put it on the table, add your favorite beverages and snacks. And you're just about to start playing, and then the doorbell rings. So you go and open it up, and there's a crowd of people coming in. So you extend the board, when you start playing, and after a while the doorbell rings again. Another bunch of people come in, and you extend the board game again. And eventually, the whole house is crowded with people. The whole house and yard, whatever, is covered with one huge board game. And as you play this game, it's so fun, so you don't want to stop. So you play day out, day in, year round. I guess this is what our CEO had in mind when he was thinking about our latest game. So say we have 100 to 500,000 players at the same time in this game. Different platforms, different versions. And by having this many people in the same room, in the same house, you won't be able to understand what they are saying, or at least most of them, because they will be speaking Japanese or French or some other language you didn't learn in school. So we need to fix that. So we need to have something to fix the language barrier, make sure that people can talk to each other. In our case, that was translation. And after we released our game, I have seen other big companies that you all have heard of starting to introduce this as well. So when you have this kind of game with tons of people playing all over the world, and it starts out small, you want to start out small because you want to see that you don't have you didn't do anything strange, or when you fix some bugs that you had, or some behavior that you didn't anticipate. But you want to scale out, and so you either can add new machines or bigger machines, whatever. But you need to be able to scale out. You need to be distributed and need to be partitioned, because all of a sudden one of the hosts goes down, or the network for that site goes down, but you want the game to still be up and be able to play it. And you preferably don't want to do that manually. You want it to automatically scale and stuff. So what are we using Erlang for at Machine Zone? We're using it for real-time world updates, real-time events, real-time timers, real-time one-to-one chats, real-time group chat, real-time translations, real-time event processing, real-time notifications. You see the theme here, real-time. So this is our chat client that we're using in the game. You have some of those, you can see there's an original text. That's what the person who actually sent it. So the one who sent it was typically saying something in English, and the device is in French because the translation is to French. Here's another one. The big seat there is that's the crown jewel for everyone. That's the thing that everybody in the game wants to sit on. That's the main ruler seat, right? And they have in the middle one picture. See, there was a war rally towards this city, And when the fight is over, apparently he won because the city doesn't burn. They're all dispersed home back again. So imagine you're in this calm little place. You found your corner in the game. Apparently very close to the wonder, which is we have the one big world, and we divided it up in kingdoms so to spread out the action. And all of a sudden, people start teleporting in, and they are bombarding the wonder, trying to take it. So from calm to really, really busy. And during this period, we can't have any lag or anything. If someone is attacking, they need to be resolved in the order as the game sees it, not the order as... And that, the way the game sees it, that's the way you need to see it as a player. Need to fix that. Okay, I have a little demo. How do I play this? It's supposed to be playing. Okay, backup plan. Oh, how do I make it? You don't see anything? Oh. This. Det ska man kan köra den istället. Den? Ja. Vill du ha ljud på den här? Nej. Perfect. Thank you. So in this picture, we have lined up a few iPads, and I'm going to see a scout going over from one to the other one, and they're pretty nicely synced, right? All the way over. There's one. And here's a sync for the chat system with the translations. Yeah. Okay. So back to our side of this. So the challenge that we face when we need to do this. We need to have the architecture support to be able to scale out and fail over and all that kind of stuff. Having everybody in the same room, everybody getting the same view, everybody being able to communicate, no language barriers. This is nice, but all of these things need to feel natural to you when you're playing a game. If you have a chat system and it takes a 2-second delay for the other person to send a message to you, it won't be a natural dialogue, right? It's the same thing if this famous, if your device is showing something that the server doesn't think, that you think your device was the first one to this resource tile, and apparently you were the second one. If the game resolves it in a way that you don't, that doesn't match what you see, you're going to be irritated in this game. You wouldn't like to play it. So we need to fix this. Another thing is having downtime means lost revenue. This is a free-to-play game. Everybody can download it. All of you should download it. But if you want to get ahead of the game, you're able to do so. You can play the whole game without spending a dime if you like to. But if you want to get ahead and then you can do so by paying us money, so that means we get some revenue. If we have downtime, that also means the people get a little bit irritated by the game. It's not available when they want to play it, so they want to switch game, play something else, and maybe they get hooked on that instead. We don't want that, right? And also when it comes to translations, if you want to use any of those translation systems out there, like Bing or Google or something else, all those translations are based on what you can say. When you read the book or read a paper, the translation for that is pretty good. But in our case, we're having a chat system, and having Google, Bing, or whatever translate chat systems, it's not really their ballpark, but it's our ballpark, and we need to solve this. We need to fix this. So the approach we have taken for all pieces of our game is that if it doesn't scale, we can't use it. That means that's the first thing we solve. We don't. If we have, in my case, I had quite early on in Machine Zone, I was developing this thing, and I had a few bugs in the functionality, but I haven't solved the scalability yet. And after a while, one of the head people there came and asked me, Fredrik, what's up? Why don't you fix these bugs? And since we need to fix scalability first, that's what I told him. He was okay with that. And next week, I have solved it, and we also fixed those bugs. So it's really, really good. And if you wanted to have a nice performance, you need to know what you're aiming for, because you can sit there and make optimization after optimization, and after a while, you do more optimization that is actually needed, at least at this stage of the game. So you need to have the goals you need to set, and also so you can scale away those things that are unnecessary. Another thing, for more like an operation case, we always have a fallback. We had one time we had the game was down. We were doing maintenance, and as I said in the early slide, you don't want maintenance, right? You want to get out of the downtime as fast as you can. But our main plan didn't work. It started to extend the time for this downtime, and we really didn't want that. So luckily, we had a fallback plan. So when we saw that things weren't working out, we were able to switch to a fallback plan and get the game up again, and then analyze and see what it was that went wrong after we got the game up. Because we don't want to fix those things during downtime. You want to fix those afterwards. And another thing we also had was during our development phase, you need to see since we need to fix the scalability thing first, we need to be able to see what the game is doing, how the game is performing in different aspects. So we need to measure, and we need to benchmark it and stress test it and failover test to find all those bottlenecks and operational issues that that our game was having. So and when we did that, we iterate, improve, see, did it scale, did it work, etc., etc. So now I'm going to give you a short example. So let's see. This is going way faster than I was thinking. Okay, so this is one of our services, the event processing service. So if you take this and boil it down to the minimal core part of this for scalability point of view, you have some typical distribution pattern. You get some payload to the distributor, and it picks a worker and it forwards over. Okay. pretty standard, right? So at the point that I was starting working with this, we had a third-party pool library to do this. And the way it was set up, we had a distributor and a set of workers. And when the distributor got the message, as fast as it could, it was sending that over to the worker, regardless if the worker had anything to do or not. So you can see that the queue for things being worked on live both in the distributor and in the inbox of each worker. This means that since we, just as the password said, let it crash, we want to have the workers crashing in case there is something bad, because you want to have a cleanup and you want to start over, setting up the new state connections or whatever it is that the workers need to do its job. But you don't want that to cause message loss, right? Because if you put the tech stuff in the inbox and the worker dies, all of that is lost. And there's also another thing. Since we're having a distributed system, the information that the worker has died, there's a slight time period until the distributor knows this, and that can be the reason for that is the distributor may have stuff in its mailbox already, so it might process a few messages before it sees that the other process is down. And then, as in this case, we're using PIDs to send for the workers instead of named workers. So it meant you can send a message to a dead PID and you wouldn't know that it was lost, right? So that was one of the goals for this iteration. Make sure we don't have a message loss and was push-based. And we want the workers to crash in case of failures. It needs to be fast. And we wanted linear scalability up to the number of cores. And there was also demand to, say that the worker dies. That's one thing. Then we should be able to solve that so that we don't get a message loss. But if the node goes down, we don't want to lose all those messages, especially not those messages that have a $sign attached to them. So we did this iteration a few times. And what we realized was that we wanted to separate control messages from traffic messages. So that, say that you have a worker that sets up a connection to some service, sets up a socket to some service. And you want to listen to, you get this TCP closed message. Then you want to prioritize that message in front of all the traffic messages, so you can kill the worker and being restarted and set up a new connection, and then you want to pop the work, right? So you don't want to lose any message because you don't have the ability to work on them. So what we ended up doing was implementing an if queue. So actually adding a new queue, so it was a lockless multi-producer, multi-consumer queue. With the option to mmap that to a file. That was how we store the persistence thing. And I must say, working with NIFs in this regard was kind of nice, because you don't need to, except for the mmapping thing, you don't need to do any special things to store your Erlang term into some structure of yours. And we were using NIF resources, so we had a separate process to own these resources. So the distributor and the workers would ask the owner for which queue to use. And in this setup, we can have the worker pop one message at a time. And if it failed, we could have a try after clause to try catch clause to log failed messages and do something else with them later on. and some number there. Implementing this NIF queue, we were able to get half the performance of Erlang message passing. And we could probably improve this a bit, but at that time it wasn't necessary. The contention among all processes were pretty low. Basically, we're using atomic operations. So it's not zero, but it's low, really low. And it scales linearly. Another thing we tried first was also to have the NIF queue being implemented in a separate thread, NIF thread. But we saw that we got 10 times better performance if the execution was actually done in the scheduler thread. So that's what we did. Yeah, another thing. We didn't have any timeouts in the call to the NIF. So that meant that we could have a receive statement to see that if we have any control messages in the inbox, and we could use the after clause to pop things from the traffic queue. So if you pop something, and you try to pop something, but the queue is empty, and you try immediately again, that would just overflood the scheduler, especially since we didn't have this counter thing for NIF calls. Yeah. So when you pop the queue, we needed to have a timeout before you try again, if it was empty. Okay. Then we were done. We're doing the other things. So time for iteration 2. We need a similar solution in a different project. We saw that having no message loss and a push-based system basically means that when the system gets overloaded, you either need to drop messages, which we don't want, or we need to add backpressure to tell the user that they need to talk to someone else, right? If you pair backpressure with the ability to auto-scale, like set up a new node if you need to, do that really quick, or have one standby, or whatever solution you want to have, then you wouldn't get any performance degradation either from the client side. We also had requirements to be able to put the persistence of the queue off the host that it's running on, because sometimes the host goes down, and you don't want to having to go there manually try to pick them up and then set them up again, because you want to write code, right? You don't want to have operational things. You want to solve that, have that automatic. We also needed some more quality of service options, like fire and forget, and best effort and guaranteed. So guaranteed would mean you need to resend in case of errors, at least a couple of times. And we also had, since our system was growing, we saw that we had application A running on these hosts, these nodes, and we have application B running on these nodes. And if one of those nodes running application B were going down, we don't want the application A to automatically stop using that for a while and try once it connects back again. So that meant having a NIF queue and then the simple worker solution that we had in the beginning, it didn't really match. So we were initially starting to reuse what we had and see that if that worked. So we broke out the NIF queue and the pooling stuff into a separate library. And but as you know, using a NIF is always a risk if you have some bug or anything. And you also have the new requirements. They supersede the old ones, so that having back pressure was more important than having speedy distribution. Yeah, I told that. Yeah. And we still don't want the worker to have any traffic messages in its inbox. At least never more than one. The one that they're supposed to work with. So it turned out that the queue was actually better that it was living on the Erlang side than in the C side. And this was the solution that we came up with. I have the client or user or whatever you want to call it do a synchronous call to the dispatcher. And the dispatcher would do a synchronous call to the queue to get its queue. So it would select one of the queue. Say that you have in the message it's saying that what quality of service you want. So and how much you want to pay for the service or how much, so forth. So then the dispatcher can choose which queue to send to. They would all do the same work, but they would have a different number of workers. Then the dispatcher would do a synchronous call to the queue, and then you get the message back. And there's a point here to having the synchronous call mechanism. It's provided the clients with some level of back pressure, because the dispatcher and the queue they can't flood those inboxes. So the same client would have to wait a while until it can do another one. And then when once the message is queued, the queue can assign the work to an available worker. And once that's done, once the worker is done, it sends the message back. Okay. So you see that there's the NIF queue. With the NIF queue solution, using that as a send mechanism, we had half the performance of Erlang send. And at the time when I was testing this, I could do, if I remember right, 3 million requests a second. So that means with Erlang send. So with NIF queue, it was 1.5. And with the new solutions, we could have, when does that become? 100,000 something a second. And depending on the number of workers, the actual work to distribute the messages is increased. So this message, this measures only the amount of work it takes to send the message to the queue, and for the queue to have the work done in a worker. And the reason why the times go up, it is not what you want, right? You want it to go down, right? So, but in this case, the workload the worker is doing is 0. It just receives the message and says it's done. So it only measures the scheduling, the message passing part. And the reason it is increasing in time is because we're using list key search, list key take. So when the worker returns, let's see, where am I? How do I point in this? Anyway, so when the call gets to queue, it just pops from queue. Thank you. Yeah, thanks. When the queue gets some work, it just we're using a queue, the queue module, to pop some work, and that's pretty fast. But when the work is done, we're putting all those that busy work in a list. So we're using, when the work is done, using key take. And with an increasing number of workers that is ongoing work, you get an increased time there. Let's see. Oh. Okay. This went way faster than was anticipated. Yeah, so we know what we needed to build. We knew that we needed to solve the scaling first, and measure and benchmarking was a big part of the development process. And yeah. So, any questions? Yes?
Okay, so you switched from NIFs to ordinary Erlang.
Say again?
You switched from NIFs to ordinary Erlang messages.
Yes.
Yeah, and how did you solve persistence then? You couldn't mmap the Erlang messages.
That's true. That's true. Yes. So it. Yeah, actually, we haven't implemented that part yet. So yes. Since we're having that in the Erlang process, the idea is that we should have a persistent connection to some external service that does this for us. And the reason we haven't solved it is because we haven't needed it yet. Or if we want to, we can have some mmapped feature for just the file storage thing. But it's not solved yet.
Okay, so if no more questions, thanks very much indeed.
Okay, thank you.